here is a problem on how the law of conservation of momentum is applied to problems, is used in solving problems on collision of objects. The problem says, let's read the problem. Problem 1 says two people, A and B, person A and person B, of masses 70 kilogram and 50 kilogram respectively. Person A has a mass of 70 kilogram, B has a mass of 50 kilogram, and this guy with velocities, A has a velocity of 6 meters per second and B has a velocity of 8 meters per second along the directions as shown in the figure. And here is the figure. Look at body A here with the mass, and this is the velocity. Body B, mass, and this is its velocity, and they collide at this point. Okay, so what is the question? They say they collide and hug each other after collision. What is their velocity after collision? Since they hug each other, this velocity is a common velocity. A has the velocity, B has the velocity after collision. Then the fractional loss in kinetic energy. This means that the collision is inelastic. If it is elastic, then the kinetic energy will be conserved. But because it is inelastic, the kinetic energy is not conserved, and we are asked to get the fractional loss in the kinetic energy. But in any kind of collision, momentum is always conserved. Now, how do we get the velocity? If you rely on the value of the velocities only, on the values of the velocity given, you are wrong. You have to consider the masses as well. This is because the masses pretty much affect the motion. So what we will do now is we will apply the law of conservation of momentum. How do we do that? Look at this one. This body A, let's say its velocity is v1 and body and its mass is m1. If we go to B, let's say its velocity is v2 and its mass, this is its mass, is m2. And additionally, we are taking upward as positive and downward as negative, and then right as positive and left here as negative. So let us look at body B. Body B is, even though it is here, but it is moving in this direction, okay, not downward, so this velocity is positive. Similarly, body A, even though it is here on the left, but it is moving along this direction, the plus x direction, so this velocity is also positive. Also, we know that the momentum is in the same direction as the velocity, so the momentum of body A is also a vector in this direction, and its value is m1 v1. Okay, v1 vector. All these velocities, they are all vectors. So this is the momentum of A, and the momentum of B is also a vector in the direction of B with the magnitude m2 v2. You see, so we have two vectors here. This is the momentum of A and the momentum of B. It's better we rely on this since they have masses of the object rather than the velocities that do not have the mass. This will give us the correct result and not just relying on the velocities and ignoring the masses. Okay, let's see how we can do that. We are going to draw the vector diagram for the momenta. Okay, the momentum of A, don't forget, is to the left like this. Okay, so we are going to draw that, and is m1 v1 vector, m1 v1 vector, and we know that the mass of A, look at it here, is 70, and the velocity is 6 in meters per second. So we are going to say 60 here times 70 here times 6, and then we bring our calculator and do that as quickly as possible. 70 times 6, and this will give us 420. So the momentum here is 420. What is the unit of momentum? Kilogram meter per second. Kilogram for mass, and then meters per second for velocity. Then the next thing is we draw the momentum, the vector for the momentum of body B, and is in this direction, upward. Remember, body B is moving upward, so this is its momentum. So we will draw it here, you see, and it is m2 v2, and this will be our mass for body B is 50 and its velocity is 8, so we're going to say 50 here and then multiplied by 8. And what do we have? You bring your calculator and say 50 times 8. Okay, when you do that you get 400. So our result here is 400, and the unit is kilogram meter per second. Kilogram from mass, meter per second from the velocity. Now the resultant velocity is here. You see, this is to tell you that the resultant momentum, is here. This is the resultant momentum. From here, this is be the tail, and then this is the head. When you are drawing resultant vector, remember, you draw it from the tail of the first vector. This is the first vector, this is its tail, this is its head. So you start from the tail of the first vector to the head of the last vector. This is the last vector. So this is the resultant. And now this resultant, how do we get the magnitude of the resultant? So we apply the law of conservation of momentum. According to the law of conservation of momentum, it says that total momentum after collision is equal to total momentum before collision. So now we ask ourselves, after collision, they have what do they have? Common velocity. The velocity is the same. So let that common velocity be capital V. If it is capital V, then it means the total momentum we have here, the momentum for A will be m1 capital V, this is a vector, plus the momentum for B, body B is m2 capital V. Is common to all of them. This is equal to, now before collision, look at the momentum of A. This is m1 v1 vector plus m2 v2 vector. You see, now from here, since v is common to them, we can factorize and bring the v out. Then we have m1 plus m2, and this is equal to m1 v1 vector plus m2 v2 vector. Now, why am I doing this? I'm just trying to show to you that since this diagram is the momentum diagram, and you can see this is the momentum of A, and look at it here, and then this one is the momentum of B, and look at it here. You added them by vector addition and you got this one, and this equation tells you that when you add this to this, this is what you will get. So it means that what I have here is m1 plus m2 v vector. You see, v vector. So if this is the case, it means that my m1, don't forget, is 70, and then my M2 is 50. So if I add 70 to 50, I will get 120. So this means what I have here is 120 V. That's the magnitude, 120 V. So from here, using this diagram, I can apply Pythagoras theorem. You can see this is a right angle triangle, and this is the angular direction for the resultant momentum. So using Pythagoras theorem, we can now say the hypotenuse squared equals the adjacent squared plus the opposite square. So my hypotenuse is 120 V. I will now square it. Okay, I removed the vector arrow to show that this is the magnitude of the vector I want to find, and this is equal to, here we calculated the momentum here and we got 420. So we say 420 squared plus, and we calculated for this and we got 400, and this should be 400 squared. Interesting. Now what do we do? 120 squared is what? From your calculator, just press 120 and you square it. That will give you, look at it, 144. So I'm going to write here 14400. Then the velocity should also have the square, because this means everything in the bracket has square. 120 has the square and it gives you this. Then the velocity, you don't know it, put V and then the square. This is equal to 420 squared. What is your result? A pretty much a large value here. But for simplicity, I can just do that directly from the calculator and say 420 squared plus 400 squared, and this will give me 336 400. Then I will divide both sides by this, so I have v square equals what I have here divided by the coefficient of v square, 336,400 divided by 14400. Okay, clearly the two zeros here cancel, but because I know some people have issues with mathematics, I'm going to ignore that. You will now say v is equal to square root. What you have to ignore, because here has a square, you can see you have a square and we have to eliminate the square. So we take the square root of both sides. If you put a square on this side, a square root on this side, square root on this side, the square root will cancel the square here and you have the v alone without the square. Then you have here on this side 336,400 divided by 14400. Okay, how do I get this directly from the calculator? Using this CAPEC calculator, I can do that directly. I will just say, I will press the square root. You see, this is my square root. Then I open bracket. Before anything, I open bracket, and then I will now press this 336,400. So I have 336,400, and I divide it by the denominator 14400. After all this, I now close the bracket. I close the bracket. After closing the bracket, then I press the equality sign. Here it is. When I press the equality sign, look at what I have. Correct to 3 significant figure 4.83. So my V is 4.83 meters per second. My V is 4.83 meters per second. Now, with this, I have successfully solved for A, because A says I should get their common velocity. You see, velocity, find their velocity after collision, and we say that the velocity should be a common velocity because they collide with each other, they stuck with each other after the collision. Okay, for B, problem B says we should get the fractional loss in kinetic energy. So kinetic energy is not conserved, so we are going to get the total kinetic energy before collision. So total kinetic energy before collision is equal to, we are going to add the kinetic energies of A and B. The kinetic energy of A is half m1 v1 squared before collision, plus the kinetic energy of B is half m2 v2 squared. Now this is equal to half multiplied by m1, and our m1, don't forget, is 70, m1 for A and m2 for B. This is 70 and the other one 50, so we have 70 multiplied by v1 squared. Our v1, look at this here, 6, so we write 6 here, but the formula says we should square v1, so we squared it, plus half times m2, and our m2 is 50, so we have 50 here squared, then times v2. What is our v2? 80 meter per second, so this is 80, and then the formula says we should square v2, so let's square that. Okay, now I would like to do this directly from the calculator, because in physics what is important is you write the formula, correct substitution, correct result. The evaluation, this long evaluation, is not necessary. Make sure the formula is correct, make sure your substitutions is also correct, and then your result after the substitution. So this one you can do it using the calculator. I know that 1 upon 2 is just 0.5, so I will just say 0.5 multiplied by 70 multiplied by 6 squared. Can you see? Multiplied by 6 squared. Then after that I have plus then 0.5 multiplied by oh my god, we put a square here. This is wrong. So we have 50 multiplied by 50, then multiplied by, oh my god, I have to ignore this one. There is no square here, and this is 8 and not 80, so 8 squared. Okay, so we have 0.5. You see everything. Now you can press equality sign, and this is your result, 2860. So this is equal to 2860 in joules. Now this is the total kinetic energy before collision. After collision, what is the kinetic energy? Total kinetic energy after collision. Okay, after collision they have a common velocity, so what you will do is you add their masses, m1 plus m2, then you now square the common velocity. So this is their total kinetic energy after collision. So this is half multiplied into m1. M1 is 70 plus m2 50, and then multiplied by the velocity, the common velocity we got. What was it? Where is the common velocity? Okay, look at it here, 4.83 meters per second. So we put that 4.83, and then we square it because it says we should square that. So this is equal to, okay, let me show you that again. You wrote the formula, the you made correct substitution. Now what is your result? You said half is 0.5, so 0.5. Now you can open bracket after that. Can you see open bracket? Then you say 70 plus 50 in the bracket, and you now close the bracket. So you press multiplied by then 4.83, and then you have a square on top of it. This is the square, so we have square here. Now you can press the equality sign, and this approximately correct to the nearest correct to when you approximate this one to whole numbers, you are going to have 1 should be added to this 9, and then this will give you 1400. So I have 1400 approximately in joule. Okay, wow. So you can see that the kinetic energy has reduced from a total of 2,860 joule to a total of 1,400 joule. Where is the remaining? The remaining kinetic energy has been transformed into other forms of energy, like sound energy when they collide, and possibly heat energy or light as well. Okay. Now, how do we get the fractional loss in kinetic energy? This is what you will do. You say fractional loss in Ke is equal to change in Ke divided by what? Total Ke before collision. Total Ke before collision. And this is equal to change in Ke divided by total Ke before collision. And this is equal to the change in Ke. You see this one minus this one will give you the change in Ke. So you open bracket here. In the numerator you say 2860 in joule minus what? 1400. So this is the change in Ke divided by, then in the denominator you have total Ke before collision, and the total Ke before collision is 2860. So 2860 in joule. Okay, again I can use my calculator and do this one without any problem. So you just open bracket, and say 2860 minus 1400, and you close bracket. Then you say divided by 28. You see, after all of that, you see open bracket, then you close bracket. Now 2860, and you press the equality sign. This will give you 0.510. Can you see 0.510? This means that if you want to get it in percentage, you just multiply it by 100. If you multiply this result by 100, you will change it to percentage, and it will be 51%. This means that 51% of the energy is lost. At the end, the two bodies move with only 49% of their initial total energy. Only 49%. Okay, 51% is lost, and I said it's being transformed into sound energy, heat energy, because if you touch the two bodies, for example, there may be heat produced, okay, and possibly light energy. Okay, so this is the end of it, and I hope you understand this problem pretty much well. But before I close, I have to tell you that if you make a mistake and consider velocities only and ignore the masses, you have a wrong result. Okay, the masses affect the resultant velocity. If you consider only velocity, you may say, okay, I have this velocity here, this is 6 meters per second, and then I have this one here, and this is 8 meters per second, and so their resultant is here. This should be their resultant velocity v, and then you use Pythagoras theorem and say v is equal to square root of 6 square plus 8 square, and then you bring your calculator and say, okay, I have the square root, open bracket, 6 squared plus 8 squared, then you close bracket. This will give you 10 meter per second, 10 meters per second, and this is very wrong. This is very wrong. You have to consider the masses. You see, when we consider the masses, at the end, what did we get? The velocity is only 4.83 meter per second, to tell you that the masses of the bodies affect the velocities. But if you ignore it and you get 10, by that you mean even if this one is 1,000 kilogram and this one is maybe just 2 gram, the velocity will still be 10 meter per second, and this is physically inadmissible. In practice, it is wrong. So you must consider the masses, and therefore you have to resort to momentum diagram where you have the masses involved. I hope this is pretty much clear. Assalamu alaikum wa rahmatullah.